Well, thank you, Nazli, for the invitation. I am really thrilled to be able to talk to you about my work and interact both with the faculty and the students at your department. Today, in this talk, I'm going to give you an overview of some of the work that we've been doing recently in the area of fairness, accountability, transparency, and ethics, FATE. And specifically because I have background in information retrieval and social computing, my work focuses on information systems specifically. For the purpose of this presentation, because I'm going to be talking mostly about information systems such as search or recommendation or personalization, let me just provide a brief depiction of what I mean by an information system. In information systems, very often we have two distinct groups of users. So these are users whom we very often call consumers and users whom we call producers. The system mediates the interaction between these two different groups of users. User who is a consumer very often has certain information needs that they want to satisfy through a particular system. So they interact with the system through an interface. The service provider operates an algorithm that ranks or classifies or recommends data from an underlying corpus. And that corpus contains documents or the profiles of the users whom we call producers. That sounds very abstract, but just to give a specific example of a system that follows the schema, a search system is an example of a system like this. So in a search system, we have a user whom we call a searcher, who has an information need that is very often expressed in the form of a keyword query. That query is passed on to the service provider through an interface. The service provider operates an underlying ranking mechanism that orders either documents or users from an underlying corpus and returns this ranked list to the searcher. And what is the form of mediation of the system in this specific example? It's that the search subjects are exposed to the searcher, and in return, searchers pay attention to the search subject. So attention can be seen as a form of currency in a system like this. Why is this important? Because many systems nowadays, for example, job portals like LinkedIn, mediate the interaction that in a way that has very specific impacts on people's lives offline. So the attention that job seekers get from recruiters can translate to monetary gains in the real world. So it's super important to make sure that this mediated interaction is fair, or in general, we avoid different types of harms or problems for all of the users in the system. And my work in general asks the question, what can go wrong in systems like this? So we look very broadly at different types of the users, for example, users as consumers, users as producers. We look at different types of the problems that can appear in different places in this pipeline, for example, in the interaction, in the interface, in the algorithm. And we ask ourselves, how can we prevent these different types of problems and harms, and how can we adapt the systems to make sure that they avoid running into these different problems. And the types of problems we're thinking about can be categorized into a number of different categories. We're looking and are interested in the societal impacts of those systems, and the societal impacts might, for example, include preventing marginalization, preventing discrimination. We're thinking about society as composed of a number of different groups. These groups are very often determined by certain sensitive attributes, such as gender or race. And we want to make sure that the system does not marginalize or discriminate groups that were historically subordinated or marginalized. Beyond societal impacts, we're also interested in looking at individual impacts. And these can include things like individual fairness. So making sure that every single user in a system gets an outcome that they deserve in the results that the system delivers. We also want to make sure that we care about user privacy for users in these different roles in the ecosystem, and so on and so forth. So individual impacts are another category of problems we're thinking about. And then when it comes to interventions, so what do we do to actually prevent the harms and prevent the systems from exhibiting discriminatory effects or invading users' privacy? There are different types of interventions. So we can, for example, impose legal constraints that they then need to be operationalized in a sort of technical computational way inside the system. We have certain societal constraints. So we as society might make normative assumptions or normative claims and say that, for example, we want the system to be individually fair. And then we have to operationalize these societal goals within the system. And then finally, we might want to say that we don't want to make any intervention. We think that the system has negative impacts that are beyond repair, and we want to refuse to build certain technologies or deploy certain systems. And I want to start this presentation with talking about the work that falls into this first category, that is how do we operationalize certain legal constraints. And this work is an interdisciplinary work done in collaboration with Michelle Fink, who is a legal scholar from the MPI for Innovation and Competition. And it's sort of an example of the work that many of us do in the FATE team at Microsoft Research. So we are a group of researchers thinking about the social responsibility in socio-technical systems. And we approach these problems from many different angles and many different disciplinary backgrounds, including different areas of computer science, but also different disciplines outside of computer science. So let me jump into talking about our specific work in the area of operationalizing legal constraints. So on a very high level, the contribution we're making here is related to the tension between extensive personal data collection for users as consumers in personalized information systems, and our ability to personalize the results of different services. Why is there a tension? We would like to limit the collection of the data because when we collect a huge amount of data about the user, we're creating opportunities for different types of breaches. When, for example, the infrastructure is compromised, we create opportunities for the system to infer information about the users that is not there explicitly. So there are many different risks involved with collection of large amounts of data about the users. On the other hand, this data is useful to learn about who the user is. And when we know better who the user is, we're able to better understand what their intents are when they're interacting with the system. And as a result, we're able to better tune the results. And this question has been around in the literature for quite some time now. So for example, in 2008, Krause and Horvitz demonstrated that data collection in the context of personalized search exhibits a diminishing returns property. That is, the more features we collect about a user, the less extra utility we gain with each feature as measured globally across all the users. So the plot that is borrowed from the work I just mentioned on the x-axis presents a number of features that were used to personalize the results of search. And on the y-axis, the utility of this data in delivering better quality of the search results. Some of our own prior work also stumbled upon this trade-off. In our CGIAR 2017 paper, we examined this problem on a more fine-grained per user level. So specifically what we showed was that we can split and merge the data of different users, creating synthetic profiles that are less and less similar to the original user profile. So in this plot on the x-axis, as we go to the right, we're creating user profiles that are less and less similar to actual user profiles. And we actually show that we're able to avoid drastically hurting the individual quality of the personalization. So individual dots in this plot correspond to different users. And as we go up on the y-axis, we're losing quality. So first of all, we show that there is a trade-off because the ideal area of this plot would be here. So and it's sort of empty enough for the legend to be here. At the same time, the actual loss that we got was relatively low. And so all of this is sort of a common thing in all of these prior lines of work is that they show that you don't need exact user profiles to get the results you want, but they do not answer the question of how much data do we actually need and what is the data specifically, which pieces of data specifically do I actually need to get certain quality of the results. And so this is a question that we started working on a while ago. And through conversations with scholars working outside of computer science, we discovered that there is a parallel between this question and one of the requirements of GDPR. And this requirement specifically is the requirement of data minimization that comes together with requirement of purpose limitation. So what this requirement says is that personal data shall be adequate, relevant, and limited to what is necessary in relation to purposes for which they are processed. So it seems like on the surface, the question on the left and the question on the right are really exactly the same question, but just phrased using the language of two different disciplines. Now, through the conversations with the legal scholars, we realized that generally it is unclear what the processing purpose for the data is in the context of personalization systems. And the takeaway from these discussions was that a purpose such as improving user experience is generally not specific enough. So now the question is, how do we define the purpose in the context of personalization systems so that it's computationally operationalizable? So we as computer scientists can take this definition and be able to translate it into code. And this is something that we tackled in a paper that we published earlier this year at SIG-IR. Our goal was to provide specific computational interpretations to these requirements of purpose limitation and data minimization. We focus specifically on the recommendation systems in our experiments, but generally these principles apply broadly to personalization systems. And we asked 3 questions specifically. So first, what is the purpose of personal data collection? Second, what does it mean to limit the data in relation to that purpose? And third, if we follow these interpretations, what would be the trade-offs and consequences of data minimization for the entire ecosystem? When it comes to answering the first question, that is, what is the purpose of personal data collection? We started with the following observation. So in personalization, personal data is collected not necessarily to actually deliver the service, but to improve the service, right? So I can provide people with non-personalized recommendations that are, for example, computed based on popularity of different items on average, and that can be estimated from data sources outside of the system. So if the purpose is to improve the service, and we as computer scientists generally measure whether things are good or bad through various performance metrics, our proposal was to tie the processing purpose to improvements in performance metrics. Now that we have this interpretation, the second question is, what does it mean to limit data in relation to the purpose? And in this paper, we proposed 2 different interpretations, but other interpretations are possible, and it's actually an interesting area of future work. So here we proposed so the first interpretation that we proposed, which we called global data minimization, suggests that we should minimize the data of each user such that we limit the loss in the model performance as averaged over all the users. So we don't care about utility loss to individual users, but we only care about preserving the average performance of the system. The second interpretation takes a more user-focused view. So in this interpretation that we called per user data minimization, we suggested that we should minimize the data of each user, but in a way that will limit the loss in the model performance also for each user. So now that we made these translations from these legal principles to things that we can actually computationally tackle, the question is, what consequences would these interpretations have? And this question was the main topic of our experimental investigation and this work. So let me tell you a bit about the experimental setup that we had. As I mentioned, we run this study in the context of recommendation systems. And we use the MovieLens 20 million dataset, which is one of the standard datasets in the recommender system research. The structure and assumptions of our study were as follows. We assume we have a recommender system that can be trained on some background system data. So that data can be either historical, so collected by the service provider before they started minimizing data. It can be purchased or, say, collected from another market that doesn't need to follow the same requirements. And in our experiments, we assume that these recommender systems are either based on k-nearest neighbor recommendations or matrix factorization, such as SVD. Then we have a set of users for whom we want to actually minimize the data. And a portion of this data will be selected to be presented to the recommender by different minimization strategies. And a portion of this data will get minimized out. And we, of course, keep a separate test set to measure the impact on the actual recommendation predictions. So what are some of our first findings? What I'm plotting here are sorted RMSE error values, and RMSE is one of the standard measures used in recommender system evaluation that looks at differences in the actual prediction values for all of the items in the test set. So I'm plotting here the sorted values of this measure for the population of all the minimizing users. When the system is a k-nearest neighbor recommender, and a user k-nearest neighbor recommender. And here specifically, as a minimization strategy, we're just selecting n random items from the minimizing user profiles. Different colors in this plot correspond to different minimization intensities. So how many items we actually choose from the user profiles to present to the recommender. The black line here shows the performance of the recommender system if we don't minimize at all. So how would the recommender, what would be the quality of the recommender if it was able to access all the user data? And now the pink and the brown lines here show the performance of one item oracles. So those tell us the upper and lower bounds of error in this data set when we select only one item from each user profile. And there are two high-level observations from this plot. First, it looks like on the population level, the error distribution remains relatively stable as we minimize. So the shape of all of these curves remains fairly similar. And second, it seems like for this particular recommender at least, we can minimize out a large portion of data, for example, leaving just 7 or 15 items in each of the user profiles, while keeping the quality of the recommender quite reasonable. But the question is, can we take these results and make a sort of policy recommendation saying, look, you actually don't need to collect all of the data, just leave 7 items or 15 items in the user profile. So we wanted to see how robust these results are, depending on different factors. The first factor was, what happens if we actually don't use a KNN recommender, but an SVD recommender, so based on matrix factorization? And it turns out that SVD, which is a matrix factorization-based algorithm for recommendations, is even more robust to minimization. So we wanted to get an understanding of why that is the case.
Yeah.
And
Mr. Leach's request for update.
So was there a question? That makes someone just unmuted. Okay, so let me give you some intuitions for why that is the case. When we are using a user-user KNN recommender system, the way we're computing the predictions of the ratings is that we compute a weighted sum of the ratings for the items in the user neighborhood. So we're taking the users that are most similar to a given user, and we average their ratings for a given item and weigh it by the similarity of the user for whom we are predicting and the user from the neighborhood. Now, when we're minimizing the data of the user for whom we are making the predictions, so the image of the user changes. And as a result, pretty much everything in this equation will change. So the set of neighbors of the user might change, the actual values of the ratings for a given item might change as a result, and the relative similarity between that user and the user in a neighborhood might change as well. So this seems relatively unstable to minimization. Now for the SVD recommendations, the values are more stable. So in a high level, the way SVD works is that we have a matrix with rows corresponding to users and columns corresponding to items. And we want to learn a factorization of this matrix such that we find latent factors, and we find user preferences for these latent factors, and we find how these latent factors describe different items. Now, without going into much detail, what we can look at is how we're updating, how we're computing the predictions here, and how we're updating the gradients when we're using gradient descent to actually compute this factorization. So what we find here is that the item biases, so this is this factor, and the item latent factors, and these are these factors, the updates to these terms will mainly come from the system data. And in our experimental setup, the system data does not change. So as a result, there is generally much more stability in the prediction with the minimized data for SVD. Now, is this enough to make certain policy recommendations? It turns out that not necessarily, that we also need to understand what data specifically we use to derive these results and this recommendation. So what we found that in the particular movie length data set, there is a relatively low variability in the rating scores. There is relatively low variability in the rating scores, and ratings between 3 and 4 on a scale of 10 make 61% of the data. So when we're using a measure such as RMSE to see whether we can minimize, in general, the absolute values of the predictions will not change that much when most of the data has relatively low variability in the absolute values. So let's also briefly talk about our insights into per user data minimization. So it seems like in general, global data minimization is feasible, but is it feasible for each user? So what I'm plotting here on the right is exactly the same data as what I'm plotting on the left with random minimization for KNN recommendations. But now the data points are sorted only by the error value of the full data predictions. That is the black line. And the errors for other minimization methods are mapped to the corresponding users on the black line. So when we look at this plot vertically, all of the error points correspond to the same user for a given X value. So we can see a huge variability in the additional error that is incurred by minimization for different users. And so what did these plots tell us together? It seems like minimization is feasible globally, and the error distributions remain relatively stable on a population level, but this hides disparate impact to individual users. Now the question is, can we predict who these users are going to be? we ran a regression analysis to try to examine whether there's any correlation between the error delta that is incurred by minimization and certain characteristics of individual user profiles. And those characteristics included things like the number of overall ratings, the average rating value, the average popularity of items, number of genres in the profile, average similarity to all system users, or average similarity to 30 closest system users. And interestingly, we found no strong correlation between any of these characteristics and the error delta. Instead, what we found was that there are complex interplays between individual user characteristics, the population data, the base recommendation algorithm used, and the minimization algorithm. So for instance, we found that for SVD recommendations, if we minimize the data by selecting the item with the highest rating, the incurred error will be higher for users who generally give low ratings. While if we select the ratings with the lowest value, the error is going to be higher for users who generally give higher ratings. And so this shows the difficulty of deriving sort of uniform recommendations or policies for data minimization. So to sum up this part, in this study, there are three main takeaways from the study. So first, global performance-based minimization looks feasible, but when we look at the performance for users, the feasibility of minimization is not that straightforward. So different users might be disparately impacted by minimization, and in general, it seems hard to tell who these users are going to be. And different algorithms differ in their robustness to minimization. What is still needed to figure out to be able to further make data minimization practical in the context of real systems is examine different definitions of purpose limitation and data minimization that are viable both computationally and legally. We need to importantly figure out how to automatically minimize data for personalization. And we need to understand and measure which users and communities might pay most in terms of service quality when we minimize the data. It is quite possible, for instance, that populations that are marginalized will be further marginalized by data minimization because the system generally has fewer data about those populations, and the populations that are about whom the system has more data will perhaps be able to sort of offer each other, to contribute the data to each other's performance more. So it's a very complex question that is important to answer when we want to minimize. And when it comes to the second question, that is automatically minimizing data for personalization, one key question that the definitions or the interpretations I talked about require is that we need to know what the potential performance would be for the system if it observed the entire data. It's one of the challenges of actually automating data minimization. And just to give you a sneak peek of some work that that we did this summer with an intern I mentor at MSR, we try to design methods that could automatically learn a stopping criterion for data collection in the context of personalized recommendations. And this method was based on an observation the deep learning community made a couple of years ago, where they found that in general, performance of different algorithms follows different stages. So there is what they call the small data region, and that is where collection of additional data always improves the performance. Then there is the power law region, where there is a trade-off. So we might want to make informed decision about whether we want to trade more data for improved quality. And then there is the irreducible error region, and that is the region where the collection of new data does not improve the performance of the model at all. And we observed a similar trends in the context of recommendation data sets. And so without going into detail, just to give you sort of intuition of what we did in this work is that we tried to fit a curve of a similar shape to the data that we observed from the users as we collected the data and as we tried to minimize the data. And that allowed us to sort of predict what the possible best performance might be for the algorithm. A sneak peek of some of the results, we were able to find the methods that came close to the prediction of the best possible algorithm performance. So the red line here corresponds to the best performance of a recommendation algorithm on the full data set. And the green curve corresponds to the best method we were able to find for predicting what that best performance might be. And so we're able to get pretty close to the prediction of the actual performance with even 50 or 60% of the data. And that sums up the data minimization part of my talk. But I also want to give you a sort of an overview of other types of problems we're thinking about. Specifically, now I want to focus on discovering the exposure context for the search subjects. So the exposure of search subjects to searchers happens in a specific context that is determined by the query the searcher issued. So for instance, on a platform like LinkedIn, when a searcher is a recruiter, they might issue queries such as machine learning engineer, and the context is positive. So all the search subjects want to be displayed as a result to that query. In the context of a platform like Twitter, for instance, the query might be something sensitive, so related to diseases or some politically charged topics, or contain personally identifiable information. So in this case, the context in which search subject would be found would be very sensitive and problematic. So as a result, the search subjects might want to sort of restrict their visibility of the data to particular queries or remove certain contents from their profiles and so on and so forth. So it's really important to understand for a given search system that ranks either your content or your profile, what are the queries that potentially expose your content, your documents to the searchers. And as far as I know, there are no search engines that really do that. I mentioned very briefly what types of exposure contexts might be of particular importance to the users. I mentioned the part personally identifiable information, for example, email addresses or phone numbers. I mentioned queries that are topically sensitive, so related to, say, diseases or politically charged topics. The queries might be surprising. So, for example, if your profile is returned as a result to a query that does not match your profile exactly, you might be surprised and you might not want it. You might be returned as a result to a query that generally does not match the topical distribution of your profile. So for example, if you have a professional account on Twitter, you might want to be exposed to queries that match this professional content, but perhaps not posts that are less relevant to the professional content. And finally, some queries might be highly monetizable in certain contexts. So for example, queries related to job searches on LinkedIn. And as a result, people might want to be displayed high in the results. And there are lots of use case scenarios for computing and telling people about these search contexts, about these exposing queries. So this can be used as a privacy awareness, audit, and transparency tools. So people might want to restrict the visibility of the content matching their exposing queries. This might allow them to ask service providers to remove them from search results in a more granular per query way, rather than just telling they don't want to be included in the search results at all. We might prevent the leakage of information through search queries, as an example I'm going to talk about in a second. We might also want to use this exposing query identification tool as a search engine optimization tool. So in a context of a platform like LinkedIn, we might be able to quantify how attractive or effective our profile is when we know what types of queries we would be exposed by to searchers. or we might want to demand that service providers distributes exposure fairly to queries we care about. And I mentioned that there are actually real-world incidents in which personal user data was leaked to searchers through the search engine. A couple of years ago, I think in 2018, there was a breach of Facebook that was not Cambridge Analytica, but happened around the same time. So what happened there is that hackers were able to scrape the public data of most of Facebook users. And the key challenge for doing this is actually being able to enumerate all of the users in the system. So what they did is they acquired a database of email addresses and phone numbers in the dark web and issued those as search queries to the Facebook search engine. And as a result, Facebook returned the links to the profiles of the users to whom these personal identifiers belonged. So this way, they were able to create sort of a database of all of the user profile URLs and get access to all of the data that was available there. So to be able to compute these contexts, the question that we would need to answer specifically is, what are the queries that expose any of my documents as a ranked subject in the top results as searchers inspect the ranking? And so this is a problem that we first defined in our second paper in 2017, and this summer also worked with students on another take on this problem in this context of embedding-based search systems. So the problem that we tackle here is what we call exposing query identification. This computation of query rankings. And those rankings are such that the queries that are at the top are the ones that are most likely to expose the particular user in the search results and are most problematic in a given application scenario. So when a searcher issues a query and my document comes up somewhere at the top in response to that query, I would like that query to be ranked high in the result of the exposing query identification system. When it comes to modeling search exposure, here's an interesting observation. So when we think about search, we start with a query, and for a given ranking algorithm, we return a list of ranked documents. Now, what we want to do here is we start with a document, and for a given search system, we want to compute a ranked list of queries that would expose the documents in the top K results of the system. So that means that computing search exposure context orders expose specifically in the context of search engines that rely on explicit embedding spaces, where we have queries and documents that are jointly embedded in a given space, we can think of as search as a nearest neighbors search, and exposing query identification as a reverse K nearest neighbor. Now, the problem with modeling it this way is that KNN and reverse KNN are not symmetric. So for this query, for example, this document or my document might be the closest, so this query would expose me. But when I look for the nearest neighbors for this document in this space, I would find these two queries, and I might not notice that this query is exposing me. So in general, we cannot use this embedding space of document retrieval to compute the exposing queries. Just to give you an intuition of an idea we pursued this summer, is we approach exposing query identification as a metric learning problem. And we try to transform this document retrieval embedding space into a new embedding space so that KNN in this new space would approximately correspond to RKNN in the old space. In general, these sorts of computations of exposing query identification face two problems. So one is computational, as I mentioned, and another one is that if we want this tool to be actually useful to the users, we might run into an information overload problem. In the first paper that we had on this topic, we worked with a number of user profiles from Twitter. And when we computed the sets of exposing queries that exposed user documents, say in the top 1, top 10, top 20, top 30 results, we found that there were users who were exposed by thousands or millions of queries. So the y-axis on this plot shows the log of the size of the exposing query sets for different users. This is problematic. We couldn't just throw a million queries or thousands of queries at the user and say, oh, here's your exposing query context information. So it's super important to actually consider this problem in the context of specific application domain. And either rank the queries in the outputs of the exposing query identification system so that they correspond to certain priority queries have in the given application domain, or filter the queries upfront even before we compute the exposure. And before I close, I want to just briefly mention another example of the work we're doing now in the context of interventions that operationalize different societal constraints rather than legal constraints. And this work specifically looked at how user interfaces might impact equality in the outcomes on different platforms. Specifically, what we were interested in is looking at certain user behaviors and user preferences and how they might be amplified or encouraged through different interface design. So we run a study in the context of a donation online charity platform. It was Donors Choose, which is a platform where schools can publish crowdsourcing projects, for example, to finance a school field trip or new equipment for the classroom. We were interested whether we can change the behavior of the donors through simple interface interventions so as to be able to channel more funding towards schools of higher poverty level. We tried a number of different interventions, and one intervention was simply removing a search box from the top of the page that enables people to search for projects according to location. So either the name of a city or a zip box. And what we found when we ran this experiment on Amazon Mechanical Turk with a control group that sees the original website and a treatment group that sees a website without a search box is that people start to donate to schools that are farther away from where they are located if the website does not give them an option to search by location. And the reason why this is the case is that people have a certain preference for donating to schools that are closer to them. The reason being is that you want to support your local community or perhaps the community where your kids go to school and so on and so forth. And why this finding has a significance in the context of fate research. It is because location is very often correlated with the poverty level of the school. And so if I'm a donor that lives in a wealthy location, I perhaps have more money to donate. If I donate to schools that are closer to me, then I'm going to donate to schools that are perhaps needed less than schools that are farther away. So this is a factor that a website that designs user interfaces and user interaction should take into account if they want to satisfy certain societal goals of the platform. Another thing we discovered as another intervention we tried is displaying additional information about the school to the donor as they inspect the ranking result. And in this case, our treatment condition was a condition where a person could see the poverty level of a school. And we found that just by showing this specific information, we were able to direct many more donations to schools of the highest poverty as compared to schools of lower poverty, and when comparing these treatment and control conditions. And finally, the third type of interventions that we might want to do that I mentioned at the beginning is refusing certain technologies instead of trying to fix them. And in this line of work, earlier this year at the FACT conference, which is the flagship conference for the fairness, accountability, transparency, and ethics in AI and socio-technical community, we organized a session where we invited people with different disciplinary backgrounds to discuss the framework that we might use to refuse technologies at an early stage as students, as engineers. So not only refusing technologies at a large scale after they're deployed and ready, but in our everyday practice, when we're, for example, asked to use a certain data set, when we're asked to add a certain feature to a system, or when we're asked to deploy a certain system. To be able to do that, we need to find sort of frameworks that would organizationally empower people to raise concerns at very early stages of the development process of technology. And similarly, if you're interested in sort of getting to know how people approach this, recently there was a great conference at Berkeley, the Refusal Conference, and some of the recordings are also available online. And this sums up my talk. I gave you an overview of the work that we're doing in the space of fate, looking at social impacts and individual impacts of the systems and trying to design interventions either through operationalizing legal constraints or societal constraints. We're interested in understanding the limits that the algorithms place on how these interventions, whether these interventions are successful or not, but also looking at how human constraints and human biases play a role in how successful our interventions are. And in general, overall, we would like to design systems that respect their users and contribute overall to their well-being. And I think there's lots of great work to be done in that space, and it's an exciting space to be. Thank you, and I'm happy to take any questions.